Okay, thank you for the introduction, and many thanks to first pronounce my name in my home country version. So, good morning. I'm Tang Xulong from Penn State. Today I'm going to present work from our group, enhancing computation-to-core assignment with physical location information. So today we're having a lot of data-intensive applications. For example, both the training and inference network in the deep neural networks, large-scale data analytics, real-time audio-video processing, as well as virtual reality and gaming. So most of these applications are very performance and quality of service demanding, so they are parallel running on many core multiple systems for acceleration purpose. However, the delivered performance rarely keeps up with the growing number of cores. So one reason behind is the cost of data access. So actually, the data access cost can dominate the execution time of most parallel applications running on many core systems. This is due to several reasons. For example, the non-uniform and long data access latency, the underutilization of compute resources, as well as the massive on-chip network data movement, which consume a lot of the energy of the on-chip network. So one way to elevate this problem is that people are reinvestigating the execution paradigm which were proposed like decades back. It is called near data processing. So the essential idea of near data processing is bring computation to the place near the data instead of the other way around. So in this paper, we're motivated by the observation that the end-to-end data exercise performance is very crucial to the data-intensive applications running on many core systems. And we found that the massive data movement on the on-chip network degrades the performance a lot. So near data processing is one of the keys to solve this problem. However, the software works targeting near data processing are still in their infancy because they're limited to either certain class of applications or certain types of architectures. So to this end, we propose a software approach that uses the data location information to generate the computation-to-core assignment with the target of minimizing the data access cost. So before moving to the motivation and details of our proposal, let's first take a look at the background. So in this slide, I'm giving a 9x9 many core systems connected through the mesh on-chip network. So each node here contains a core, a private L1 cache, and in the private last level cache system, it's just another private last level cache, and in the shared last level cache system, it contains a last level cache bank. And let's also take a look at the data movement caused by data access in this mesh architecture in the shared last level cache systems. So suppose the data request is missing the local L1 cache. The request is going to the remote node which contains the corresponding last level cache bank. And if it misses in the last level cache, the request will be forwarded to the corresponding memory controller, and the data is fetched all the way back to the requesting node. So obviously, it depends on where the data is and the location of the requesting node. The access latency and the data traveled on the on-chip network is also different. So come to the motivation, we use the same mesh network before, and this time we are trying to parallelize a loop, simple loop body into 4 chunks and running them in parallel. Because there is no data dependency here, so we can just simply chunk this loop into 4 parts and annotate it here, use different colors. Let's further assume that the data accessed by a chunk of the loop body are going to the corresponding memory controller. They are missing the last level cache, and they're going to corresponding memory controller with the same color. So if we map the computation in a way like this, for the right one, the off-chip exercises are going to the right top memory controller, and the data are fetched all the way to that node. And similarly, for the blue one, it's going to the right bottom memory controller, and the data is fetched to the left top node there. And this is the same thing for the rest 2 chunks of the data. So the observation here is that instead of mapping this chunk, for example, the red chunk of the loop body, instead of mapping it to the node showing here, we can map this chunk to a place which it is near the memory controller too, such that the requests are going to traverse less distance, and as well as the data will be fetched from nearby place. Similarly, we can do for the rest of 3 chunks of the loop, such that the data movement is reduced on the on-chip network. So move to the shared last level cache system. It's a similar concept here. So the misses from the private L1 cache will go to the L2 cache, and it misses here will go to the memory controller and fetch the data back. So if we can map this computation to the place where it is near the last level cache bank, so the not off-chip accesses, but the L1 misses are going to traverse less distance as well. So as a result, the distance traveled by data accesses is reduced. So the benefit of doing so are twofold. First, the latencies are reduced for all the data accesses, and also the probability of the on-chip network congestion. So in able to do this kind of a smart computation mapping, we need to answer three critical questions. First, what location information are needed to guide such kind of computation mapping? Second, how do we get this data location information at compile time from the software level without modifying the hardware? Third, how do we use this location information to get the computation? So to answer these three questions, I will first give the high-level overview of our proposal. So the first question, what kind of data location information are needed here? So to target this question, we propose four concepts to capture the data location information. They are basically the affinity of computation to memory controllers, the affinity of cores to memory controllers, affinity of the computation to last level cache banks, and also the affinity of cores to the last level cache banks. So the computation here basically are loop iteration sets, means a bunch of loop iterations. So for the second question, how do we get this data location information at compile time? So we apply the cache miss equation, which is very famous in the compiler area, to the loop nest in the application, and apply it on the static nucleus system to get the data location information. We also modify the operating system page allocation API to make sure that the last level cache bank base and memory controller bank base are preserved between the virtual address to physical address translation. So with this affinity vectors in hand, we define and use the difference between affinity vectors to get the computational assignment, such that the data movement is effectively reduced. So we target both the private last level cache system and the shared last level cache system. And in our benchmark suite, we include both regular and irregular applications. So at this moment, I want to emphasize our target or our goal here. So for private last level cache, we want to perform a computation to core or to the node assignment such that the off-chip exercises are loading data from the nearby memory controllers. Similarly, for the shared last level cache system, we want to map computation to cores such that both the local L1 cache misses are fetching data from nearby last level cache banks, and off-chip accesses are fetching data from nearby memory controllers. So now let's dive into the details. So the first affinity vector we define is called memory affinity of iterations. It basically captures the affinity between loop iteration sets and the memory controllers in the system. So recall the figure I just showed in the target slice. So this MAF vector actually captures the affinity between the computation and corresponding memory controllers in the system. So giving an example with the loop here, let's assume that every exercise is basically missing the last level cache, and AI is going to memory controller 3, BI and CI are going to memory controller 1, and DI is going to memory controller 2. So let's also assume that there are 4 memory controllers in the system. So the corresponding MAI vector is set to 0.5, 0.25, 0.25, and 0, indicating that half of the exercises are going to memory controller 1, and 1/4 are going to memory controller 2 and 3 respectively. So the higher value in the case precision of the MAI vector, the stronger affinity between iteration set I and memory controller K. So the second affinity vector we define is called memory affinity of cores, which is MAC vector. It captures the affinity between cores and memory controllers in the system. So recall this figure here. So the MAC vector basically captures the relationship between the core and memory controllers. So it can be simply just expressed as the Manhattan distance between the core location and their corresponding memory controller location. However, in practice, we divide this mesh network into regions. So for example, recall we have a 9x9 manifold system. So we divide it into 9 regions, and each region contains 3x3 cores. So this is based on the observation that the nearby cores have the similar preference to a given memory controller, and the benefit of doing so is we try to avoid the workload imbalance across cores. So basically, we are trying to assign computation to regions instead of to individual cores, and within the region, it's basically in the workload in a round-robin fashion, such that the workload is balanced across cores. So the example, let's look at the region 2 here. The MAC vector basically is 0.5, 0.5, 0, 0, indicating that region 2 is equally close to memory controller 1 and memory controller 2, but far away from memory controller 3 and memory controller 4. So with this MAI vector and MAC vector, we are now able to perform the computation assignment in the private last level cache system. We define the difference between two affinity vectors. Let's assume that we have two vectors, delta and delta prime. So the difference eta is basically the summation of the absolute entry level difference divided by the total number of entries in the vector. So the lower difference between two affinity vectors, the higher similarity between them. With such a kind of a difference definition, we can just explore the difference between the MAI vector for each loop iteration set and the MAC vector for all the regions. And we find the region gives us the smallest value of the difference, and this is basically the right place we map this loop iteration set. So the eta basically captures the computation-to-core mapping here. So move to the shared last level cache systems. We need to define another 2 additional affinity vectors to help us have the location information between the L1 cache and the last level cache banks. So the CAI vector basically is called cache affinity of iterations. It captures affinity between loop iteration sets and the position of the corresponding last level cache banks. So recall this figure I showed in the target slides. So the CAI vector basically captures where the computation, which last level cache bank the computation is close to. So it's an n entry vector, and the number of n is determined by the number of regions in the system. So the jth entry in the CAI vector indicates the strength of affinity between this iteration set and the region J in the mesh system. So the example here, we use the same example, but this time we assume that every access is going to hit in the last level cache bank. So let's assume that AI is going to the last level cache bank in region 2, and BI and CI are going to region 4, and DI is going to region 8. So the corresponding CI vector is all there except the second position is 0.25, the fourth position is 0.5, and the eighth position is 0.25, indicating half of them are going to region 4 and going to hit the last level cache banks in region 4. So similar to MAC vector, we define cache affinity of cores. It captures the affinity between cores and last level cache banks. So it's also an entry vector to match the number of entries in the CAI vector we just discussed. So basically, the CAC vector captures the affinity between the cores and last level cache banks here. So for all the cores within the region K, the case entry in the CAC vector is set to 0.5. In the paper, we explore different weights to this entry of the vector, but for explanation here, I just use 0.5. And the remaining affinity is equally distributed across the immediate neighbors of this region. So the example, let's look at region 1 here. So the first entry is set to 0.5, and the second and fourth entry are set to 0.25 and 0.25, indicating that region 2 and region 4 in this type of in this space is the immediate neighbor of region 1. So with all 4 affinity vectors defined, now we're going to perform the computation assignment in the shared last level cache system. We define the eta m as the difference between the MAI vector and the MAC vector, and the eta c represents the difference between the CAI vector and CAC vector, and the eta m basically is the optimization for the last level cache misses, and eta c is the optimization for the last level cache hits. And in realistic, it's very normal that in a loop body, some of the accesses are going to hit in the cache, some of them are going to miss. So we define, we need a weight factor here, which is alpha, and we define our final function eta as alpha eta c plus 1 minus alpha eta m. And the alpha is definitely between 0 and 1. So basically, the eta here captures the computation-to-core assignment in this diagram. So now let's look at a more realistic example. So in this same loop, assume AI and DI are going to miss the last level cache. They are going to memory controller 3 and memory controller 2. And BI and C are going to hit in the last level cache in the region 4. So the corresponding MAI vector is set to, with the second entry and third entry to 0.25, and CAI vector is all there except the fourth entry is 0.25. So alpha is set to 0.5 because half of the accesses are going to hit in the cache and half of them are going to miss. And we're trying to minimize the target function, which eta equals to 0.5 eta c and 0.5 eta m. So we find a common solution, Rk, which gives us the minimum net value of the eta, and this is basically a region we should map this iteration set. So come to experiment setup and evaluation. In the paper, we evaluated 21 multi-thread applications contain both regular and irregular nested loops. And we evaluate both on the real hardware, which is Intel K9 Landing Zen 5 coprocessor with different cluster modes and flat memory mode. We also use a simulator called Gym5 to provide detailed statistics and also the scalability sensitivity analysis. So here I just show the results from the simulator. And the top part is for the private last level cache configuration. And the bottom part is shared last level cache configuration. The black bar here represents the reduction in the network latency, and the yellow bar here represents reduction in the execution time, basically the performance improvement. So as one can observe here, across all the applications, so we're able to reduce the network latency by 38.5% in the private LLC system and 48.3% in the shared LLC system. And this translates to the performance of 10.9% in the private LLC system and 12.7% in the shared LLC system. So for more results and discussion, you can refer to the paper. Come to conclusions. So in this paper, we see that data access cost due to the massive on-chip data movement degrades the performance of application parallels running on the medical systems. And near data processing is one of the keys to elevate this problem. So we propose a software approach, maps the computation with the information of the data location to minimize the data movements on the on-chip network. So evaluation shows that our approach can effectively reduce the on-chip network data movement in both private and last level private LLC system and the shared last level cache system. So that's all for today. Thank you, and I'll be happy to take any questions.
Other questions? I can warm up by asking clarification questions first. So what would be your main competitors right now of this system?
You're seeing from the, what's the competitive of the K9 Landing kind of
No, I mean,
system?
what would be of your technique? Are there other compiler-based techniques or anything? What's the closest thing that you would
Yeah, actually, while we perform this research work, one important thing is that we're trying to map the computation such that it's near the data. But one may just to say that why we don't perform some smart data layout transformation such that we can map the data smartly to the closed memory controller. So actually in the paper we did a comparison and we did a combination as well to say that how both approach compare to each other and how they can, if I remember correctly, the average improvement plus the layout optimization is another additional 9 or 10% improvement across all the applications.
Qasim from Rutgers again. I have a short question about That's, I mean, affinity makes sense that you consider when you are doing optimization. But another point is that I'm not sure if you consider or not is that routing algorithm that happens in that mesh that you are talking about. Let's say when you're talking of affinity, basically just saying the neighborhood, but neighborhood depends on the routing algorithm as well. So are you considering that routing for the on-chip? You don't know it, just do it obliviously.
So if I understand correctly, your question is basically what is the routing policy we use on the on-chip network,
Yeah,
right?
that's
So actually we use static routing, which is YX routing, and we believe that in the modern many-core systems, the static routing is used a lot because the dynamic routing is too complex, and also the scalability is not that good as static
so,
routing.
I mean, even so you assume that you know what kind of static routing you are using, and based on that, you are defining that affinity and all
Yeah,
that.
so basically we're using the YX routing in the
Okay,
static
thank you.
YX routing.
Thanks.
Thank you.
I will follow up. No. We need a couple more minutes. So I'll follow up with you had some, in your evaluation, you had regular and irregular loops. So there's a dual question. First of all, how irregular were your irregular loops? And second, based on that, what's your worst case? So if you do really, really badly, if your cache-miss equations are horrible, will you do, on average, just as well as random assignment, so you don't really lose anything with your technique?
Yeah,
or will you
actually-
do catastrophically bad?
Yeah, actually, that's a very good question. So you see that cache miss equations applies very well in the regular loops with basically regular pattern of exercises. But for irregular application or irregular loop body, so what we apply is basically it's called inspector and executor execution paradigm. What it does is that in the application, usually you have a very outermost loop, which is called a timing loop. And internally, you're performing your work, and the timing loop is just checking whether your results is meeting some criteria or it's terminate to the the preset, the maximum of the iterations. So the inspector executor execution paradigm basically at the beginning of the timing loop is trying to sampling the stride, trying to sampling the statistics, and then it's basically using this information to derive the rest of the loop execution. So we saw that in the Coral benchmark suite, actually, you see this inspector executor actually also needs some pattern. It's just that compile time you're not able to figure out, but it still needs some runtime regular pattern there. Actually, in the Coral benchmark suite, we see that our approach applying our approach, we got like less than 5% improvement. This is basically because that it's not predictable, the behavior. And also it takes a long time for the inspector to generate such kind of information. So the runtime overhead is very high.
But the bottom line is that even if you mispredict, you're not going to do worse than random assignment.
Yes. Thank you.
Let's thank Shrilong again.